InterConnect is an exciting new project where you are able to develop new services regarding energy management, as well as integration of electric mobility in our car park. Sonai companies are leading the pilot demonstrations in 12 stores where several services will be demonstrated. One of the use cases regards the provision of flexibility to the grid operator, taking advantage of the existing flexibility in the HVAC systems and cooling systems in our tertiary buildings. We'll also test innovative EV charging strategies as part of our convenience services, responding to the needs of our clients in terms of electric mobility. We will also enhance the integration of PV solutions, making sure that our stores are increasingly more positive. Projects like InterConnect are essential to break some of the existing technological barriers and demonstrate the solutions and its potential.
Sonai MC, as end user, will test and validate the technologies that are being developed in 12 different stores within our group, where we are deploying them to support our commercial pilots. Based on the results, Sonai MC could replicate the ones to other Sonai stores or even to other business units within our group to leverage and consolidate our sustainability corporate strategy as well as the decarbonization of the energy sector.
The continuous adoption of load-intensive distributed resources such as electrical vehicles or heat pumps and renewable energy sources such as PV or wind is increasing the pressure on electricity grid by introducing extra variability and uncertainty on both demand and supply sides. So there is a clear need to develop new strategies to then prepare and counteract these problems introduced in the system by the new distributed resources. This can be accomplished with the activation of the inherent flexibility of certain electrical loads that can provide an increase or decrease in power consumption during a given time interval in the future. This can then be used by DSOs to mitigate potential congestions in the grid through a more active management approach of these flexible resources. In the end, the use of demand-side flexibility can also be much more economically favorable than traditional sources, such as flexible generation, while also allowing the DSO to defer some network investments, improve the integration of distributed generation, and improve the overall power system resiliency. Regarding this specific use case and pilot, we'll be exploring the demand-side flexibility on the commercial level, more specifically on the supermarket stores' refrigeration systems for the Portuguese company Sonai MC. Considering the substantial thermal mass of these systems, they can also be seen as an energy storage medium that can be used to shift electrical consumption in time and provide the necessary demand response. The architecture for this use case is composed by the DSO interface from RH, the Portuguese DSO. Then we have the building operating system from Sensinov, which has here the role of flexibility aggregator. Then you have InterConnect forecasting service, which provides flexibility forecasts for a given store cold system, meaning the average power consumption increase or decrease over time upon activation of a specific operation mode. An example would be how much does the power decreases over a specific time interval upon activation of store's energy saving mode. And both of these systems can be accessed remotely by a portfolio manager. And then you have the ExoStructure building operations system from Schneider Electric, which works as a local energy management system for the supermarket store local controllers from Sonai. And both of these systems are limited to local access by a store manager. Then, regarding to the communications, the energy management system communicates with local store controllers via backnet to get both appliances data and send commands to store controllers. This monitoring data is sent to the flexibility aggregator via InterConnect semantic interoperability layer, which provides an interface towards a cluster of supermarket stores. This middle layer also allows for other third-party data-driven services to later consume supermarket store cold system data. And finally, we have the communication between the DSO and the flexibility aggregator via interoperability layer, and the request from the flexibility aggregator to the forecasting service to get the needed flexibility forecast for a specific store. Regarding the sequence of actions to demonstrate, first the DSO identifies an overcurrent problem in a medium voltage line and calculates the flexibility needs to solve it. Then the DSO sends the flexibility needs to Sensinov BOS, the flexibility aggregator, via interoperability framework. Sensinov BOS receives this flexibility needs request and checks in their system which stores can provide flexibility. Then the flexibility aggregator obtains flexibility forecasts from InterConnect Flexibility Forecasting Service and creates the flexibility offers to be sent to the DSO for approval. These offers are then received by DSO and inspected, which approves and creates the activation plan based on the flexibility offers provided by this flexibility aggregator and sends back the approved plan to Sensinov BOS. Based on the flexibility activation plan, Sensinov creates the operation mode schedule, which is then transmitted to the local energy management system from SONAI via interoperability framework. And finally, Schneider Local Energy Management System sends the operation mode schedule to SONAI MC local store controllers, which then activate later on the schedule operation mode. In the end, the DSO verifies that the grid congestion is solved with the flexibility activation from this or other stores, and the store refrigeration system returns to the default operation mode schedule. In this video, you can see an overview from the DSO of a medium voltage line in Ponte Lima, near to the supermarket, where there is a predicted overcurrent from 11 a.m. to 1 p.m. Then the DSO calculates the flexibility needs required to solve the overcurrent problem, which you can see here below. Here you can see Sensinov's InterConnect southbound connector, which allows the data exchange with Schneider local EMS via InterConnect semantic interoperability framework. In this interface, you can see the status of the connector and access the connector logs or alerts. When the connector is up and running, all the information collected from Schneider will fuel the Hypervision portal, which features all the 12 commercial pilot sites that will be accessible through the Sites menu. Clicking on a building will give you an overview of the site, featuring a 3D view of the building and its areas, and information regarding power consumption and latest activities, such as the activation of a specific cold system operation mode. Then there is a 2D map allowing users to easily interact with connected devices and get real-time information of their status and latest activity or set points. The device interface lists all the available devices for the building site, their location within the building, their status, and more. By clicking on a device, you can then access its detailed view page. This is the main page for the cooling system of this specific store in Ponte Lima, which is one of the stores that can offer flexibility by adjusting its operation mode to either power saving or boost mode. In the upper right corner, you can see an alert message mentioning that the new flexibility needs request was performed by the DSO. So we can inspect this recent request or any other requests by clicking on this alert. Right now, you can see that Sensinov platform is waiting for the InterConnect flexibility forecasts to create the final offer. Upon receiving a new request, Sensinov will request a forecast from InterConnect service, which processes that forecast. You have some logs from InterConnect API below, and then the final offer is created based on that information. You can see that once the request is complete, the status message changes to waiting for DSO approval. Sensinov will then send the flexibility offer to the DSO, which creates a final flexibility activation plan in order to activate or not this flexibility. Then the DSO sends this plan to Sensinov BOS, which then transmits it to Schneider EBO to later be implemented by the store controllers. Schneider EMS interacts with local store controllers. You can see that right now the store is operating on its default mode. Then, according to the predefined schedule by Sensinov, it will activate the power savings or eco mode, providing the decrease in power consumption required by the DSO. You can see that the cold system compressor starts to slow down, the active power consumption decreases, and the temperature of the store refrigeration system starts to increase. Finally, you can see that by exploring this type of demand-side flexibility, the DSO was able to prevent a potential grid overcurrent problem, which was solved with the flexibility activation of this supermarket cold system. In the end, the store returns to its default operation mode. You can see in this image the system changing from eco to default. The total active power increases and the temperature of the refrigeration system decreases, returning to its default values.